everyone, my name is Michaela, and today we are going to be doing a simple demonstration on uniform circular motion. So we have a cup of water here, and we're going to swing it around in a circle. And then we're going to figure out why the water doesn't fall out of the cup. To begin, let's explain what is meant by uniform circular motion. So in uniform circular motion, the object is going around in a circle at a constant speed. In non-uniform circular motion, the object is going around in a circle at a varying or not constant speed. Remember that speed is just the magnitude, whereas velocity is the magnitude and the direction. So in uniform circular motion, while the object is traveling at a constant speed, its velocity is changing because the direction of its movement is changing. So, to try and make this demonstration as close to uniform circular motion as possible, I'll have to try and make the cup move at a constant speed. So let's try it out. So here's proof that there is water in the cup. And now I'm going to swing it around in a circle. Notice that the water didn't fall out of the cup. And I have my guest here, Shadow, who is going to make sure that the water is still in the cup and that I wasn't cheating. Let's look at what keeps the cup moving in a circle. An object moving in a circle is accelerating, which means that its velocity is changing. For the velocity to change, either the speed or the direction must be changing. Our cup is undergoing uniform circular motion, so it is moving with a constant speed. It is accelerating due to its change in direction. The direction of the acceleration is inwards towards the center of the circle. We call this kind of acceleration centripetal acceleration. How do we know that the acceleration is directed towards the center? Well, we look at the change in velocity. Look at this diagram. We use the vector quantities of the velocities to find the change in velocity, and we see that this is directed towards the center of the circle. We can calculate the centripetal acceleration using the equation v squared over r, where v is the speed of the object and r is the radius of the circle. So where does this acceleration come from? For the cup to be accelerating, there must be a net force on the cup. The net force acting upon the cup is directed towards the center of the circle. The inward net force is said to be a centripetal force, and its magnitude is given by mv squared over r, or the mass times the centripetal acceleration. Without this force, the cup wouldn't move in a circle. With the inward net force directed perpendicular to the velocity vector, the cup is always changing its direction and undergoing an inward acceleration. The tension in the string is always towards the center of the circle, and it varies as we go around the circle, since the force of gravity is always acting on the cup in the downward direction, and we need the centripetal force to remain the same for the cup to move at a constant speed. We can see that the force of gravity is constant, represented by the red arrows of the same length. The tension is represented by the purple arrows of varying lengths. At the top, the tension and force of gravity are in the same downward direction, so the tension is the centripetal force minus the force of gravity. At the bottom, the tension is upward, or towards the center, and the force of gravity is downward, so the tension is a centripetal force plus the force of gravity. At the sides, the force of gravity is perpendicular to the centripetal force, so the tension is the centripetal force. Now let's look at the water in the cup. So, if the force of gravity is pulling the water downward, why did it stay in the cup? It's inertia that keeps the water in the cup. Inertia is the tendency of an object to maintain its state of motion. When the cup is at the top, the water is moving to the left, and the inertia of the water tries to keep the water moving to the left, while the force of gravity pulls the water down. This is like the water you see coming out of a horizontally oriented hose. So, as the water tries to continue along its inertial path, the cup is pushing the water, guiding it around in a circle. If the water and cup are moving fast enough, the water stays in the cup. If the water and cup are not moving fast enough, then the water will fall out. Now I have a challenge for you. The next time you are in a car going around a corner really fast, think about the physics of you being pushed towards the side of the car. I hope you all learned something interesting today. Thank you for watching.